Okay, example 6, we're going to take a look at a geometric series. Remember that a geometric series, what we covered earlier, was of the form CR to the n, where we could have some coefficient here, some real number c, but then we have every term has this common ratio, r raised to a certain power. So that's exactly what we have here, except for our common ratio is, well, the variable x. So this is a geometric series. So if we write this out, it looks like 1 plus x squared. Oops, should be a, forgot my plus sign. Plus x cubed, so on and so forth. So this should converge. So this equal sign here, this should converge to 1, the first term, over 1 minus the common ratio. This is true provided the absolute value of the common ratio is less than 1. So remember, this converges if this is true. So this equality here is only true provided absolute x is less than 1. Well, what we've done just here has essentially told us everything we need to know. We know that a regular old geometric series would converge if absolute x is less than 1, and it diverges if absolute x is greater than or equal to 1. So here we're not actually using the ratio test. We're not using the ratio test. We are using what we've already determined earlier about geometric series. These two options were the two possibilities for a geometric series, that either our common ratio is less than 1 in absolute value or it's greater than or equal to 1. So because we do have divergence when absolute x is exactly equal to 1, we know that our radius of convergence is 1 in this case, and we know that the interval of convergence is the open interval -1 to 1. All right. Example 7. Express the following function as a power series centered at c equals 0 and determine its radius and interval of convergence. So first thing I want to do is draw your attention to notice how similar this expression is to this expression here that we just worked with. In fact, we are going to exploit that similarity so that we can use this result. Work smart, not hard. So what I'm going to do here is just mention, I'm going to use a different variable just so it gives us a little bit of an additional flexibility. So the sum from n equals 0 to infinity of, let's say, z to the n, this is equal to 1 over 1 minus z, provided that the absolute value of z is strictly less than 1. So I'm really just rephrasing this equality right here. I'm just changing x for z. And the reason for this is we can perform a substitution into this generic geometric series for the specific term that we have here. So if z equals x squared, then this series here becomes the series from n equals 0 to infinity of x squared to the n. And then that should converge to 1 over 1 minus that common ratio, provided that the absolute value of x squared is less than 1. So now we'll have to examine this inequality a little bit further in order to determine the specifics as to what's going on with the radius and interval of convergence. Sometimes this changes things. Let's see if it does here. So a little fact here is that the absolute value of x squared is the same thing as the absolute value of x squared. So this inequality here being less than 1, this is also less than 1. Then, if I take a square root of everything, square roots do not change the direction of the inequality, so it stays that direction. So we end up getting the same thing here. And since, again, this is being interpreted as a geometric series, we know that it diverges when this is greater than or equal to 1. So this does give us that the radius of convergence is 1, and our interval of convergence is the open interval -1 to 1.